Graham's number, named after Ronald Graham, is a large number that is an upper bound on the solution to a certain problem in Ramsey theory. The number gained a degree of popular attention when Martin Gardner described it in the Mathematical Games section of Scientific American in November 1977, writing that Graham had recently established, in an unpublished proof, a bound so vast that it holds the record for the largest number ever used in a serious mathematical proof. The 1980 Guinness Book of World Records repeated Gardner's claim, adding to the popular interest in this number. According to physicist John Baez, Graham invented the quantity now known as Graham's number in conversation with Gardner himself. While Graham was trying to explain a result in Ramsey theory which he had derived with his collaborator Rothschild, Graham found that the quantity now known as Graham's number was easier to explain than the actual number appearing in the proof. Because the number which Graham described to Gardner is larger than the number in the paper itself, both are valid upper bounds for the solution to the Ramsey theory problem studied by Graham and Rothschild. Graham's number is much larger than other large numbers such as a Googleplex, Skew's number and Moser's number. Indeed, like the last three of those numbers, the observable universe is far too small to contain an ordinary digital representation of Graham's number, assuming that each digit occupies one Planck volume. Even power towers of the form are insufficient for this purpose, although it can be described by recursive formulas using Newton's up-arrow notation or equivalent, as was done by Graham. The last 10 digits of Graham's number are 2,464,195,387. Specific integers known to be far larger than Graham's number have since appeared in many serious mathematical proofs. Context: Graham's number is connected to the following problem in Ramsey theory. Connect each pair of geometric vertices of an n-dimensional hypercube to obtain a complete graph on two n vertices. Color each of the edges of this graph either red or blue. What is the smallest value of n for which every such coloring contains at least one single-colored complete subgraph on four coplanar vertices? In 1971, Graham and Rothschild proved that this problem has a solution n, giving as a bound 6 a per mole currency n a per mole currency n, with n being a large but explicitly defined number, where in Newton's up-arrow notation. The number is between 4 a 2 a 8 a 2 and 2 a 3 a 9 a 2 in Conway chained arrow notation. This was reduced in 2013 via upper bounds on the Haliza-Jewett number 2. The lower bound of 6 was later improved to 11 by Jeff Ixu in 2003, and to 13 by Jerome Barkley in 2008. Thus, the best-known bounds for n are 13 a per mole currency n a per mole currency n. Graham's number, g, is much larger than n, where this weaker upper bound for the problem, attributed to an unpublished work of Graham, was eventually published and named by Martin Gardner in Scientific American in November 1977. Definition: using Newton's up-arrow notation, Graham's number g is where the number of arrows in each layer, starting at the top layer, is specified by the value of the next layer below it. That is, and where a superscript on an up arrow indicates how many arrows there are. In other words, g is calculated in 64 steps. The first step is to calculate G1 with 4 up arrows between 3 seconds. The second step is to calculate G2 with G1 up arrows between 3s. The third step is to calculate G3 with G2 up arrows between 3s. And so on, until finally calculating G equals G64 with G63 up arrows between 3s. Equivalently. And the superscript on f indicates an iteration of the function, for example, far4, n, a equals af, f, 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 n. Expressed in terms of the family of hyperoperations, the function f is the particular sequence, which is a version of the rapidly growing Ackermann function a, n, n. The function f can also be expressed in Conway chained arrow notation as, and this notation also provides the following bounds on g. Magnitude. To convey the difficulty of appreciating the enormous size of Graham's number, it may be helpful to express a euro in terms of exponentiation alone. A euro just the first term of the rapidly growing 64-term sequence. First, in terms of titration alone. where the number of 3's in the expression on the right is. Now each titration operation reduces to a tower of exponentiations according to the definition. Thus, becomes, solely in terms of repeated exponentiation towers. And where the number of 3's in each tower, starting from the leftmost tower, is specified by the value of the next tower to the right. In other words, G1 is computed by first calculating the number of towers, n equals 3 a 3 a 3a. A 3, and then computing the nth tower in the following sequence. First tower, 3. Second tower, 3 a 3 a 3 equals 7,625,597,484,987. Third tower, 3 a 3 a 3 a 3a. A 3 equals a euro. A registered trademark. G1 equals nth tower, 3 a 3 a 3 a 3 a 3 a 3 a 3a. A 3. Where the number of 3's in each successive tower is given by the tower just before it. Note that the result of calculating the third tower is the value of n, the number of towers for G1. The magnitude of this first term, G1, is so large that it is practically incomprehensible, even though the above display is relatively easy to comprehend. Even n, the mere number of towers in this formula for G1, is far greater than the number of Planck volumes into which one can imagine subdividing the observable universe. And after this first term, still another 63 terms remain in the rapidly growing G sequence before Graham's number G equals G64 is reached. Rightmost decimal digits, Graham's number is a power tower of the form 3AAN, so its rightmost decimal digits must satisfy certain properties common to all such towers. One of these properties is that all such towers of height greater than d, have the same sequence of d rightmost decimal digits. This is a special case of a more general property, the d rightmost decimal digits of all such towers of height greater than d plus 2, are independent of the topmost 3 in the tower. That is, the topmost 3 can be changed to any other non-negative integer without affecting the d rightmost digits. The following table illustrates, for a few values of d, how this happens. For a given height of tower and number of digits d, the full range of d-digit numbers does not occur. Instead, a certain smaller subset of values repeats itself in a cycle. The length of the cycle and some of the values are shown in each cell of this table. The particular rightmost d-digits that are ultimately shared by all sufficiently tall towers of 3's are in bold text, and can be seen developing as the tower height increases. For any fixed number of digits d, the number of values possible for 33AA Euro 3AX mod 10d, as x ranges over all non-negative integers, is seen to decrease steadily as the height increases, until eventually reducing the possibility set to a single number when the height exceeds d plus 2. A simple algorithm for computing these digits may be described as follows: let x equals 3, then iterate, d times, the assignment x equals 3x mod 10d. Except for omitting any leading zeros, the final value assigned to x is then composed of the d rightmost decimal digits of 3AAN, for all n, d. Let k be the numerousness of these stable digits, which satisfy the congruence relation g, mod 10k, a per mil, gg, mod 10k. K equals T1, where g, t, equals 3AAT. It follows that, G63 a per mil Ka per mil G64. The algorithm above produces the following 500 rightmost decimal digits of Graham's number. A Euro 02425957373839565793351798334535362521. 4300354012677162267221604119. 8106522631693551887880, 38814483146525264605210711720009970092. 912495443788874960628829111725. 063001303622934916080, 254594614924210291427832508292896753530, 4308699380168924989268099510. 169055919951195027887, 17308370183402647454888222165732228010132974509, 27344594333009010969280025. 3527518332898844615008, 94042826501819385619963996790549663800, 03222348723967184851864390059. 104575627262464195387. See also, hyperoperation, Ackermann function, Kruskal's tree theorem, Ramsey theorem, notes. References: Graham, R.L. Rothschild, B.L. Ramsey's theorem for n-parameter sets. Transactions of the American Mathematical Society 159, 257 €292 doi, 10.2307/1996010. JSTORA 1996010 of the explicit formula for n appears on PA 290. This is not the Graham's number G published by Martin Gardner. Graham, R.L. Rothschild, B.L. Ramsey-theory. In Rota, G.C. Studies in Combinatorics 17. Mathematical Association of America PPA 80 €99. ISBN A0-88385-117-2 on PA 90, in stating the best available estimate for the solution, the explicit formula for n is repeated from the 1971 paper. Gardner, Martin. Mathematical Games. Scientific American 237, 18 €28 doi, 10.1038/Scientific American 1177-18a. Reprinted in Gardner, cited below. Gardner, Martin. Penrose Tiles to Trapdoor Ciphers. Washington, D.C. Mathematical Association of America. ISBN A0-88385-521-6. Gardner, Martin. The Colossal Book of Mathematics, Classic Puzzles, Paradoxes, and Problems. New York, New York, Norton. ISBN A0-393-02023-1. External links: A Ramsey Problem on Hypercubes by Jeffikshu, MathWorld article on Graham's number, How to Calculate Graham's Number, Some Ramsey Results for the N-Cube. Republication mentions Graham's number, Padilla, Tony. Parker, Matt. Graham's Number. Numberphil. Brady Hare and A. Ron Graham. What is Graham's Number? Numberphil. Brady Hare and A. Ron Graham. How big is Graham's number? Numberphil. Brady Hare and A.